Hello and welcome back to Calculus Explained. Today we are looking at limits involving infinity. So what happens to a function as x approaches infinity? So far we've looked at limits near a specific point. Today we are going to ask a different question. What happens to a function as x gets really, really large? This idea leads directly to asymptotes, invisible lines that functions get closer and closer to, but never quite reach. What this looks like is, say we have a function as x gets closer and closer to infinity, the value of y approaches this line right here. So we say that the limit of x as it approaches infinity of f of x would be equal to, let's say this is y equals 0, 0. So what does at infinity actually mean? Well, infinity isn't really a number, it's a direction. When we say x approaches infinity, we're asking, what does the function do as x gets further and further to the right? We can also say something similar as x approaches negative infinity. When x approaches negative infinity, we're looking at what happens as the function goes further and further to the left. So that's what these two limits are. They're limits to infinity, or rather, what happens as x goes really, really far in one direction. One simple example might be f of x equals 1 over x. Here, this would be 1/2 of the 1 over x function. This would be the positive side. Now the negative side would look like this. Here you can see that as x goes closer and closer to negative infinity, f of x also gets closer and closer to 0, but from the bottom. Now a horizontal asymptote is what limits to infinity really tell us. So a horizontal asymptote is a value that the function approaches as x goes to infinity or negative infinity. We can say that if the limit of x to infinity of f of x is equal to L, then y equals L is a horizontal asymptote. Now let's look at some examples of this. First, limit of x to infinity of 1 over x squared. We can see that as x gets bigger and bigger, the value of this gets increasingly large. So then the value of 1 over x squared will get increasingly closer to 0. So we can say that this limit is equal to 0. This means that the horizontal asymptote, or at least one of them, would be y equals 0, is a horizontal asymptote. We can abbreviate this as HA. Now another example, limit of x to infinity of 3x plus 1 over x. We can see here that if we divide the numerator and denominator by x, we get 3 plus 1 over x over 1. Now the limit of this, we can see as x goes to infinity, this gets increasingly large, so then 1 over x goes closer and closer to 0, meaning that we can say limit of x to infinity of 3 plus 1 over x over 1 equals 3 over 1 equals 3. So horizontal asymptotes come from dominant terms, the biggest powers of x. What this means is that if we look at one case where the degree of the top is less than the degree of the bottom, so for example, limit of x to infinity of 2x over x squared. Now here you can see that this is 2x to the first. Because this first is smaller than this second, this is just going to be equal to 0. Because as x gets closer and closer to infinity, the bottom function is going to increase at a much faster rate than the top function. So if the denominator grows faster, the whole fraction is going to shrink to 0. Now, another case is when the degrees are equal. So let's say limit of x to infinity of 3x squared plus 1 over 2x squared minus 5. Here, as x goes closer and closer to infinity, this approaches 3/2. We can see that the coefficients of those x squareds, those isolate themselves into the value of the limit. We can derive this by saying 3x squared plus 1 over 2x squared minus 5 equals 3 plus 1 over x squared over 2 minus 5 over x squared. This is what we did with the previous limit. We divided each by x. Well, in the previous, we divided each by x. In this case, we are dividing by x squared. Now here, as x goes to infinity, this and this go to 0, meaning that we are just left with this, 3/2. And that gives us our answer. So that means horizontal asymptote y equals 3/2. Now our last case is when the degree of the top is greater than the degree of the bottom. We see, for example, limit of x to infinity of x cubed over 3x. Here, this 3 is going to be greater than this 1. So if the numerator grows faster, then the function shoots off to infinity. This means that this limit is equal to infinity. Now this often leads to slant asymptotes, which we'll cover later. Now a vertical asymptote happens when the function blows up to infinity near a certain x value. An example is limit x to 2, 1 over x minus 2. Now from the left, you will see that if we draw the function, we'll see that from the left, y approaches negative infinity, but from the right, it approaches positive infinity. This here is positive infinity. This is negative infinity. This means that x equals 2 is a vertical asymptote, or rather, VA. Vertical asymptotes come from the values that make the denominator 0 after simplification. So if we contrast this with wholes, for example, x squared minus 4 or x minus 2, this is a whole because you can cancel it out. This just becomes x plus 2, x cannot equal 2, which looks like this. That is different from this scenario here. In this scenario, there are limits to infinity. In this scenario, there's a whole. So let's look at some practice problems. question 1. Limit as x approaches infinity of 5x squared over x squared plus 1. Question 2. Limit of x to negative infinity of 2x over x minus 3. Now question 3. Identify the asymptotes of f of x equals 2 over x plus 1. Now try these 3 on your own. Pause the video and we'll go through them together when you're ready. Welcome back. Now we are going to go through these together. So here we can look at the coefficients 5 and 1. This simplifies to 5. That's the quick way of doing it. Now, another way of doing it, 5x squared over x squared plus 1 equals 5 over 1 plus 1 over x squared. This goes to 0 as x gets bigger and bigger, leaving you with 5 over 1 equals 5, which is the same. Now let's look at number 2. As x goes to negative infinity, we say that this is equal to 2 over 1 minus 3 over x. Now as x goes to negative infinity, this is going to be the same as if x goes to positive infinity. It's just going to go to 0, meaning that we are left with 2 over 1 equals 2. Now for number 3, we're going to identify the asymptotes of f of x equals 2 over x plus 1. Well, when does this equal to 0? When that equals to 0, that's when we know that there's going to be an asymptote. So x plus 1 equals 0, meaning that x equals negative 1 is our vertical asymptote. Now for our horizontal asymptote, we look at limits to infinity. Limit as x approaches infinity of 2 over x plus 1 is going to be equal to 0, because this is going to get increasingly large, and since the degree of the top is 0, degree of the bottom is 1. That means, by definition, this will go to 0. And from the left-hand side, as x goes to negative infinity, this will also just go to 0. So today we learned how limits behave at infinity and how asymptotes appear naturally from these limits. Next, we'll look at limits that can't be solved with algebra alone. And that's where the squeeze theorem comes in. I hope you enjoyed this video, and I will see you next time.